Hey ladies and gentlemen, it's Professor Williams again, and my goal in this video is to make you confident about confidence intervals. Really, I just want to explain what they are, how they work, and hopefully from there, you'll be able to become the champion of confidence intervals. Let's see what we got. All right. You'll remember that at some point in one of my previous videos we had a sample of bulldog puppies, and from that sample we weighed them all, we came up with the average weight and created a point estimate. That was our little puppy sample mean, and he weighed 10 pounds. And with the use of confidence intervals and point estimates, he is so cute that we can use him or her to estimate the average weight of every bulldog in the world. In other words, draw the sample, calculate a point estimate, which could be a proportion, an average, and then use it to estimate the average weight of every bulldog puppy in the entire world. Well, how the heck do we do that? Gonna show you right now. Remember we said that the central limit theorem told us that if we either had a normally distributed population or sufficient sample size that we could use our friend the normal curve to make inferences or to draw conclusions about populations from samples. Well, that's how we're going to create these confidence intervals. We're going to use our little friend over here, sample mean, our little sample mean puppy, and we're going to use his weight in this formula as X bar, because what we're saying is that X bar is a pretty good approximation of the mean weight or the average weight of this distribution, except instead of being spot on, I want you to give me a little bit of wiggle room. And when I say wiggle room, I want you to be able to let me be within a given percentage below or above the true value of the mean, because I don't want you to hold me to an exact number. Well, how do we deal with not holding me to an exact number? We create a confidence interval. And that confidence interval is simply going to be a range of values on the normal curve within which we believe the true average weight of all of these puppies is going to fall. In other words, the mean is going to be sample mean minus some amount and sample mean above or plus some amount. How do we determine then these X values on the curve? Well, it's all driven by how close you want me to get to being right. Because what I'm going to do is I'm going to tell you I can be right and I can feel confident, confidence intervals, in my response or in my estimation that the true mean falls within this interval based on the sample mean, which was this little guy right up here, based on our sample mean within a given confidence level. Sometimes we can almost think of this in terms of margin of error. So, what the heck is Z alpha A2, Z alpha divided by 2, all of this stuff here? Let me walk you through real quick what we're talking about in that part of our formula. Let's talk first about a 99% confidence interval. When I deal with a 99% confidence interval, I'm simply going to take my mean, my sample mean, and I'm going to give myself a range. And what I'm going to say is, at the 99% confidence interval, I am 99% certain, right? I'm 99% certain that the mean, or mu, of the weight of all of the dogs in the world fall between this upper and this lower value of my interval. Well, that means a 1% chance that I'm wrong, isn't it? Because 99% right is the same thing as saying 1% wrong. Well, if there's a 1% chance that I'm wrong, you know that this normal curve is a mirror image of itself, which means I can be wrong on both ends of the curve. I can be wrong high or low. So at a 99% confidence interval, there's a 99% probability that the true mean of the population of puppy weights falls in this area, and a 1% chance that I'm wrong. And we just said I can be wrong on both ends, high or low. Then, what do we also know? We also know that with that 99% confidence interval, 1% chance of being wrong, that half of my wrong answers and the other half of my wrong answers are going to fall respectively in the lower and the upper end of the curve. Z alpha divided by 2. Alpha being the area in the tail. Remember, the little fish has a tail. So alpha, right, my little fish, means the tail. Why do I take it divided by 2? Curve has two tails, doesn't it? So, in my 99% confidence interval, what I'm really saying is the Z value associated with 99% of the data, the Z value, not Z equals 99, but the Z value associated with the points on the curve within which 99% of the data will fall, and alpha divided by 2, in this case, 1% divided by 2 means that in this area of the curve and this area of the curve, I'm going to have 1%, 0.01 divided by 2 is going to tell me that I have 0.005% of my data in each end of the curve, because 0.005 divided by times 2 is going to be my 1% split between the two tails, 99% here, because the one thing we also know is that every single curve is going to add up to 1. Hi ladies and gentlemen, it's Professor Williams again. I want to talk to you about confidence intervals, estimation, and point estimates for a minute. What I'm going to use to do it is this basket full of bulldog puppies. Because sometimes, like puppies, we can't take and examine every bulldog puppy in the world. So that population is too big. So what instead I'm going to do is I'm going to use a sample of puppies, which are my puppies in the basket, and I'm going to use these little guys right here to draw some conclusions and make some sweeping statements about the characteristics and attributes of all bulldog puppies in the world. So what is the point estimate? The point estimate is simply a single value, just like this one single puppy, that is derived from the sample used to estimate the population value. So all this little guy is the sample mean. So what I did was I took all my puppies in my basket and I weighed them. And I came up with the average weight of them, and that is this little guy right here. And he is simply the single value estimate of the weight of every puppy in the universe. Well, that's a little bit of a bold statement to say that my small sample is representative of the entire population. In other words, I'm saying my basket of puppies was so well drawn as a sample that I could calculate the sample mean, and this one little guy right here becomes the poster child representative of the average weight of every puppy in the entire universe. What's more realistic is to say that the average of my sample can be used to create a range, an interval, a spread within which the true average weight of all puppies probably falls. In other words, I'm not going to use a single value or a single point to represent the true average weight of all these puppies. I'm going to use a range or an interval of values within which I believe the true population mean will fall. How confident or how sure I am that I've actually captured the average weight of every puppy in the world is simply my confidence interval. That's the 99% certain, 95% certain, 90% certain, because I'm a lot better off giving you a range of values than I am putting all my faith in this little guy, regardless of how cute he may be. So when I move and swap over to creating a confidence interval, what I do is I take my point estimate, remember my one little guy, and I make him the mean of my distribution. And when I make him the mean of the distribution, I'm then able to construct confidence intervals that are based on this guy, who is my point estimate and my sample mean. And instead of saying, hey, the population mean is exactly right here, instead, when I go to my confidence intervals, I say, based on his weight, I am a given percent, 99%, 96% certain that the average weight of every bulldog puppy in the world falls somewhere in this range, in this confidence interval. So basically what I'm doing is, instead of using this little cute guy as the absolute value of the population mean, I'm using him as the basis for constructing a confidence interval within which I am fairly certain the true average weight of every puppy in the world falls. How I determine the values that are at the end, top and bottom of my interval, how I determine that is with my confidence interval, which is basically my 95, 99, 96, 86% probability. And remember, in order to do that, we fall backwards. We fall back to our normal curve, and the scale of z. So hopefully this makes the whole concept of point estimates and confidence intervals make a little bit more sense. I'm going to work some problems in another video, but until then, this is the end. See you guys soon.
Hi everybody, it's Professor Williams, and today I want to talk about margin of error as it relates to confidence intervals. So we remember that the whole point of a confidence interval is to accurately predict the actual value of a population parameter. And this margin of error is a representation of that accuracy, and it has three components. Firstly, it has our level of confidence, which is represented either by our z alpha or our t alpha divided by 2. It's the number of standard deviations we need to move from our point estimate in order to construct the interval of interest. It's also made up of the value of the standard deviation, whether that be population or sample. And then lastly, it's made up of our sample size. Because in essence, when we go to predict a population parameter such as the mean, we're going to begin in our point estimate and we're going to go plus or minus this margin of error. In other words, the range of likely values of x is going to be estimated with whatever our desired degree of confidence is, and we're going to estimate it to be between this lower and upper boundary of our confidence interval with our margin of error equal to e. So let's take a look at each of these three components individually. First is our level of confidence. So as our level of confidence increases, the margin of error also increases. So in this case, we've constructed a 90% confidence interval. So 90% of the time, our actual population parameter value will fall between this lower and this upper limit. And at a 90% level of confidence, we have this 10% falls outside of our interval, and so I've got 5% of that data is going to fall above the upper limit and 5% is going to fall below the limit. What's going to happen though when I go to say I want to be 95% confident, in other words 95% of the time the true population parameter will fall within my interval? Well, now at this 95% level of confidence, I only have 2.5% of the data below the lower boundary and 2.5% above. So what's happened is I've begun at my point estimate and I've moved further away up and further away down, because what we know is it is point estimate plus error and point estimate minus error. So as my confidence level increases, the ends of my confidence interval move ever further and further away from my point estimate, thereby increasing my margin of error. So what about standard deviation? Remember, standard deviation is simply a measure of the spread or variation within the data. So what we know is the more spread there is in our data, the greater our margin of error is going to be. And so we can look at that with a simple example. So I have a sample size of 40, population standard deviation of 8, gives me a standard error of the mean of 1.26. But what if in my same sample size of 40 had a standard deviation of 10? Now look what happens. My standard error of the mean increases. And as that increases, I'm moving ever further and further away from my point estimate. So the larger the standard deviation, the greater our margin of error. I cannot control the value of the population or sample standard deviation, but what I can do is I can control sample size. And what we know is that as sample size increases, we're able to decrease our margin of error. So we'll look at the same example. So I have an N of 40. I take a sample of 40. Population standard deviation of 8 gives me a standard error of 1.26. But what if I want less error in my estimation? I go back and I take a sample of 60 with that same population standard deviation of 8, and now my standard error has dropped to 1.03. So as standard deviation rises, our margin of error rises. As sample size rises, our margin of error falls. So much of the accuracy in our interval estimation of population parameters is going to be determined by this idea of a margin of error based on degree of confidence, the amount of variation that exists within the sample or the population, and the size of our sample. As always, I hope that you found this useful, and thanks for watching.
Hey ladies and gentlemen, it's sample size time. Yes, it's that time when we get to determine how big of a sample we need to draw in order to be as close as we're happy with. In other words, accuracy and error is directly related to sample size. Bigger the sample size, smaller the error. We can work it either by how close we want to be or how big our sample is. So let's take a look at this real quick. Like I just said, how close to right do we need to be is often and is a function of the size of our N, or our sample size. So in this formula we have N, sample size, same thing it's always meant. Z, what is Z? Z is back to those confidence levels, those Z values that we had for those different confidence levels, for the 99, 95, remember we had 1.96 for a 95% confidence interval. We had 2.58 for the 99% confidence interval. Yep, it's the same Z value. Simply the standard normal value corresponding to the desired level of confidence. It's our good old friend sigma, and we know since sigma is a Greek letter and all Greek letters represent population parameters, you know that sigma is simply the standard deviation for the population. E, what's E? E is the maximum allowable error, how far we're willing to be off. How big the error is often determined by what we're testing or what we're trying to come to a conclusion about. If it's the price of a 3-topping pizza in my business location or in my market, I'm not real concerned about being really close. If, however, it is the percentage or the number of people who will experience bleeding from the eyes if they take my new drug, I'm probably going to want my E value to be pretty small. Last but not least, I have a square, an exponent. So, in order to determine the optimum sample size based on my allowable error, I'm simply going to take the Z value associated with my confidence level times the standard deviation of my population, divide it by the error, square it, and come up with N. Just remember, with N, we always round up to the next whole number because you can't have 0.02 of a person. So let's take a look at an example of this, and I think y'all will catch on to this one really quick. Alright, so what we have is we want to estimate the average number, so we're estimating for the mean. We want to estimate the average number of people who crash rental cars within 2 automobiles. So the population of car wrecking renters is known to be 10. So we have a standard deviation of 10. We want to be 95% certain that we are correct. So we're talking about a 95% confidence interval. So we're simply going to apply this formula right here to the information that I have. Well, what do I know? I know that Z for a 95% confidence interval is 1.96. I was just told that my standard deviation was 10. I want to be within, remember I said how close or how far off do we want to be? I want to be within 2 cars. So, in order to do this, now I'm simply going to take my 1.96 times 10. I'm going to divide it by 2. And I'm going to come out with 9.8 squared. So when I take 9.8 times 9.8, I'm going to come up with 96.04. So what that's telling me is, and I'm going to round up, I now know that I need to sample, my sample size needs, my sample size, I'm going to back off of that, actually needs to be 97 cars. Because I want to round up, because I'd like to be within 2 automobiles of being correct. That's all it is to calculating for a sample size. Because of the properties of our most dreaded friend, algebra, if I'm given n, and I'm given z, and I'm given sigma, I can now solve for the error. If I am given, on the other hand, if I'm given E and N and Z, I can solve for sigma. So I can always solve for the error or the sample size or the level of confidence or the standard deviation, provided that I've got 3 out of these 4 pieces of information. And that, ladies and gentlemen, is all there is to calculating sample size. Have an awesome day. Hey guys, it's Professor Williams again. Yep, more confidence interval stuff. Woohoo! Alright, I'm going to actually work a problem this time that has to do with the weight of bags of candy. Since this video is being made shortly after Halloween, let me show you how this is done and what it means. So, hang on and let's get going. Get out your calculators and your pencils, ladies and gentlemen. Okay, here we are. We all know that a 3-pound bag of candy doesn't really weigh exactly 3 pounds. So, what we do is we go in and we sample 36 bags of candy and we weigh them. The average weight of our candy, the sample mean, is found to be 3.01 pounds. And we calculate a standard deviation of 0.03 pounds. So, I want to know with 95% confidence, I want to be 95% certain of what the weight of all of my 3-pound bags of candy is. So what I'm trying to do is I'm trying to set of 2 values, a low end and a high end, in between which 95% of all of my bags of candy will weigh. That's the entire concept of a confidence interval, right? I want to know the upper and lower values or weights between which 95% of all of the bags of 3-pound bags of candies in the universe is going to fall. So, let me show you how I'm going to substitute in to this formula. Alright, let's see what we're going to get. Sample mean is X bar, isn't it? So for X bar, I'm going to end up with sample mean 3.01 pounds. And that's 3.01 pounds on the end, on the lower end, 3.01 pounds on the upper end. Now, what else do I have? I have standard deviation of 0.03 pounds, because I know the standard deviation of these bags of candy was 0.03 pounds. And I also know how big my sample was, don't I? I know that my N, or my sample size, was 36. So, almost done. Almost done. Now I just need to see what is my value for Z alpha divided by 2, or Z alpha, Z sub alpha divided by 2. Remember, this is the idea that 95% of my data is going to fall in between these two areas. I know from my textbook, and because Z-scores are standard everywhere, that the Z alpha value for a 95% confidence interval is always, write it down, always, always, always going to be 1.96. So I'm going to substitute in here 1.96 here, 1.96 here. Why is it 1.96 other than the fact that I just told you that it's always, always, always 1.96? It's because what this represents in terms of my curve, it means that 95% of my data is going to fall here. That's supposed to be even, so just roll with me here, guys. And if I know that 95% of my data falls here, then I know that between this end of the curve and this end of the curve is that other 5%. Remember, the entire curve equals 1. So if I take 5% and I divide it by 2, remember, it's equally divided between each tail of the curve. I know I have 0.25 here and 0 or 0.025 here. So the z-score of 1.96 is the z-score associated between this point that we're going to give a number to now and the mean, right, that contains 47.5% of the data. If you look in your z-score table, you will see that a z-score of 1.96 contains 0.4750% of the data, because 95% divided by 2, because remember, it's equal, this side and this side is equal, 95% divided by 2 gives me, let me get rid of some of this junk, gives me on each side at 95%, I end up with 0.4750 here, and on this side, because this curve is uniform, 0.4750 here. And if I use my z-score table backwards and I find the z-score associated with 0.4750% of the data falling between this point and the mean here, I know that it's 1.96. So for those of you with inquiring minds wanting to know why is it 1.96, that's why. It allows us to solve for any confidence interval, but for the standard ones, for 95, 99, 80, you can go ahead and solve once and then simply slip these values in every single time. So let me do a little bit of math magic and solve this for you. All right, what was the first thing I did? I'm going to remember my order of operations. The first thing I did was I did this exponent. I did this square root down here. Square root of 36 is 6. So now the next thing I'm going to do is I'm going to divide 0.03 divided by 6 on each side and take you one step further. Okay, so now I've taken that 0.03 divided by 6 and I've come up with my 0.005. And remember, this formula is the same on the lower end and the upper end, except for this. Remember, on the right side of the curve, we add. On the lower side of the curve, we subtract, right? But other than that, these two sides of the formula are identical. So now that I've completed this little piece of the formula, I'm now going to take 1.96 multiplied by 0.005 on each side of the curve. All right, so I did that math, and now what I know is that to get the lower limit for a 95% confidence interval, I'm going to take the mean. Remember, x bar is right here. I'm going to take the mean and I'm going to subtract it to get this value here. I'm going to add it. I'm going to add it to get this value here, right? Because this is the positive side of the curve. And so let me go ahead and do that piece for you. So now what I've done is I've simply finished my math, and what I know is that the mean, right, remember the mean is in the center. Right, what I now know is that I am 95% certain that the true weight, or the weight of all 3-pound bags of candy, is between, the average weight is between 3.0198 on the high side and 3.002 on the low side. And what that does is that lets me be 95% certain that the actual weight of every 3-pound bag of candy in the universe, if it could, every one of them could be collected up and weighed, they would all weigh between 3.0002 pounds and 3.0198 pounds. There's only a 5% chance that I'm wrong. And remember, that 5% chance is split between half of my mistakes being on the high side and half of my mistakes being on the low side. So, in conclusion, the 95% confidence interval for the weight of all 3-pound bags of candy is going to be right here. So, hopefully this helps, and I will see you guys around the chalkboard. Have an awesome day. Hey, ladies and gentlemen, it's Professor Williams again. This time with confidence intervals using Minitab. So let's get started and see what we've got. All right, so hopefully you will remember from at some point that a confidence interval is the area within the curve where we believe that the true population parameter will fall. What we have outside of the curve is, of course, alpha, where alpha represents the tail of the curve and also represents the probability that I am wrong and that I have missed the true population parameter. We come up with this alpha divided by 2 because if alpha represents the tail, then in a confidence interval we have 2 tails, hence alpha divided by 2. And so what we know is that the left portion of the curve, or the left tail of the curve, plus the level of confidence, plus the right tail of the curve is always going to equal 100%. We're just going to use our regular old z-scores, and we're going to use our regular normal distribution tables. Except in this video, I'm going to show you how to dump all of that and use Minitab instead. So what we have is, according to a recent poll of 90 dog owners, the average number of plastic water bottles that their pets chew up per year is 540. We know the standard deviation of the population of bottle-chewing dogs to be 40. We're going to construct a 99% confidence interval for the true mean number of water bottles chewed up by all dogs. So before you watch this great video, what you had to do was you had to apply this formula right here, or a version of it, where we took X bar, which in this case would have been 540. You would have taken sigma, which would have been 40. We would have taken the square root of n, which would have been 90, and we would have found our value for Z alpha divided by 2 of 1.96, and then done all this math, and we'd have added things up, but not this time. Instead, here I am with Minitab, and I've simply opened Minitab to a blank worksheet, and I want to construct the confidence interval for the true mean. So I'm going to come up here to Stat, and I want basic statistics. And what I know is that I have a one sample Z test. How do I know I have a one sample Z test? A, I only sampled those 90 people coming out of PetSmart or wherever they were, and I know I have a Z because you were given the population standard deviation. So I'm going to click on one sample Z, and I'm going to get this great dialog box. I have summarized data, which means the sample size, the mean, the standard deviation have already been calculated for me. So I knew my sample size was 90. I knew that the mean was 540. The standard deviation was 40. So that's all fine and well, except there's no button to really click for this confidence interval. I need to come down here to Options. Options is going to open a second box, and it's going to ask me for the confidence level. Ignore this alternative right here for now, because that's when we hypothesis test. I'm just doing confidence intervals. Type in this case, we wanted a 99%. Put it in as 99.0 and say OK. If I wanted to do in this case, a 95%, 95.0, hit OK. So in Options, you change the level of confidence. I've entered my summarized data, and now I need to go lay down because this is going to be so hard. I'm going to hit OK. Minitab thinks for a second, and amazingly, what it does is for a one sample Z, it assumes the standard deviation is 40. It shows my mean as 540 and gives me the 95% confidence interval for the true mean of the population of all dogs who chew up water bottles. Now, it also gives you one other piece of information that was a bonus that you didn't have to pay extra for, and this is this value right here of the standard error of the mean. When I look at that standard error of the mean, what is that? That's simply the standard deviation divided by the square root of n, and in this case it's 4.22. So if I went back to my problem, what my answer would be, it would be the 95% confidence interval is this. So I wish I had something else amazing to say, but that's all there is to it. Hope you guys have a great night.
Hey everybody, it's Professor Williams, and I want to talk to you a little bit about confidence intervals for the mean when we don't have the population standard deviation. So there are a lot of instances when the value of the population standard deviation, or sigma, is just not known. And what we know is that when the value of sigma is not known, then we're going to estimate it. And we're going to estimate it using S, the sample standard deviation. So when we knew the population standard deviation, we were able to find these standard values of Z alpha divided by 2 that were associated with the various levels of confidence. However, when S is used, in other words, we are going to estimate population standard deviation using the sample standard deviation, we cannot use standard normal distribution and Z values. So instead of our Z value, what we're going to use is we're going to use what we refer to as a T value, or in the case of a confidence interval, a T alpha divided by 2. And where we're going to get those values are from the student T distribution, most often just referred to as a T distribution. It's very similar to standard normal distribution, but has a couple of key differences. So the T distribution is similar to normal distribution in that it's generally bell-shaped. It is symmetrical, so we have a curve that is going to look very similar to our normal distribution table. In other words, it's going to be symmetrical about the mean, where we have 50% of the data above the mean and 50% below the mean. We also know that the mean, the median, and the mode are all the same and are located at the center of the distribution. And again, it's this asymptotic curve that runs out into positive and negative infinity but never touches the horizontal axis. There are a couple of key differences with the T distribution and the Z distribution. The key difference is the T distribution is actually a family of curves based on this concept of degrees of freedom, which is directly related to sample size. So if we looked at this family of curves, what we would see is that in an n of, say, 2, you would have this incredibly flat curve. And then at n of 10, you would get a little bit more normal. And at an n of 20, a little bit more normal. And by the time we get to an n of 30, we'd be looking very normal. And at an n of 50, we'd be looking very tall and very thin. And so because of this, what we know is that the area in these tails is not going to be the same for every one of these curves. And for that reason, our values of T alpha divided by 2 are going to have to be looked up in a T distribution table based on two things: our level of confidence, or our value of alpha, and our sample size of n. So when we said that our T distribution was directly related to sample size, it is also based on the concept of what we refer to as degrees of freedom. So degrees of freedom is simply n minus 1. In other words, it's the number of variables in our formula that can vary. And in this case, for confidence intervals, it will be n minus 1. So if I have an n equal to 20, then I'll have degrees of freedom equal to 19. So if my n was 25, degrees of freedom would be equal to 24. And so what we end up doing is we end up, remember, looking at our alpha. So let's say our alpha was 0.05 and we had this n of 20. What we would end up looking up is a t of 0.025. Remember, we split our alpha, our tail, into the two sides of the interval with 19 degrees of freedom. In this case, if we had an alpha, say, of 0.10 and we had this n of 25, we would look up a t of 0.05 with 24 degrees of freedom. And it's this relationship between the shape of the t-distribution curve and sample size that requires us to look up our value of t alpha divided by 2 for every different curve that we have. One of the things we do know is, remember, that even though as sample size increases, the t-distribution, remember, is going to become much closer to our standard normal distribution in terms of shape. The fact of the matter is, when we do not have the population standard deviation, we cannot use normal distribution in z-scores. Instead, we're going to use our t-distribution. For a confidence interval, we're going to take our alpha, divide it by 2, and then we're going to look it up at n minus 1 degrees of freedom. And this will allow us to accurately identify the areas in the tail and find these critical values that will help us when we go to construct our confidence interval. I know this was brief, but as always, I hope that it was helpful, and thanks for watching.
Greetings one and all. Yes, Professor Williams here, still talking about confidence intervals. But this time it's confidence intervals with a twist. Let me tell you why they have a twist. Because you're working along in your confidence interval problem, and you all of a sudden look down and say, but I don't have the population standard deviation. Well, we need the population standard deviation, don't we? Because that's what goes into that standard error, sigma divided by the square root of n. What am I going to do? I can't go any further. That's why it's with a twist. Twist with a T. Because when you don't have sigma, you'll have S, the standard deviation of the sample. And in the alphabet, last time I checked, T came after S. So you remember that S and T right next to one another. When you don't have sigma, you're simply going to use the standard deviation of the sample and then use the T distribution with degrees of freedom, simply calculated by n, sample size, minus 1. Don't believe me? Let me show you. All right, we got an owner of a farm who wants to estimate a 95% confidence interval. Remember, 95% confidence interval simply wants to know the lower and the upper range between which 95% of the data will fall, right? And what he wants to know is, he wants the 95% confidence interval for the number of tin cans that the goats living on his farm eat per week. So he goes out, he randomly samples 20 goats, finds that on average they eat 20 soda cans per day, and since he's the one who drew the sample, he's calculated the standard deviation to be 2 cans. So in order to be certain that he has enough cans lying around his farm, he wants to calculate this 95% confidence interval for the mean number of cans eaten by all of his goats. In other words, the goat population. Well, all he has is a standard deviation for these 20 goats on his farm. Well, what he does have is he has the mean, doesn't he? Right? We just said that he took a sample of 20 goats, found on average they ate 20 soda cans per day. That is X bar, right? We also said it had a standard deviation of 2 cans. That's S. We knew that he took the sample of 20 goats. That's his N. So now I have calculated and have a numerical value for everything. I have X bar, average of 20 soda cans per day. I have S, standard deviation of the sample of those 20 goats is 2. N, 20 goats in his sample. Mu, I've got everything except for this weird looking thing called T alpha. Well, as soon as I said alpha and you saw alpha Remember our little fish, alpha, little fish with the tail? The tail of the alpha is the same thing as the tail of the curve. And I'm betting that we have a table for this, don't we? Yeah, we do. Let me show you what it's going to look like. We're simply going to use a student's t-table, because since we're using the standard deviation of the sample, everything is driven by how big our sample is. So earlier in the video I said degrees of freedom, right? Degrees of freedom, DF, calculated simply by n minus 1. How many goats did he sample? He sampled 20. 20 minus 1, last time I did my math, was 19. So, first thing you're going to do, take the number in your sample, subtract 1, come up with your degrees of freedom. Next, determine what confidence interval we're solving for. Well, in this case, the problem told you that we want the 95% confidence interval. See right here where I've got this arrow? 95% confidence interval. So come down to where your 95% confidence interval is in your column, and it meets degrees of freedom at 19. Bingo. 2.093 is the value for a t distribution with 19 degrees of freedom, 95% confidence interval, 2.093. Write that number down somewhere because I'm getting ready to use it. There you go. That's all I had to do. All I had to do was drop in that 2.093 for that t sub alpha value, because like I said, since this is based on sample size and degrees of freedom, you don't have the same standard values that we did when we had sigma. Remember, I told you before, and you all remember, that for a 95% confidence interval, Z alpha sub 2 is going to be 1.96. For 99% confidence interval, it was that 2.58. Well, in the t distribution, when we do not have sigma and have to substitute S, sample standard deviation, we have to go look up our value for this t portion of the formula every time, based on sample size. So, now I'm going to fill in the blank, and I'm going to solve, and we're going to see what the 95% confidence interval is for the true average number of soda cans this guy's goats eat in a given day. Now, all I have done, through the magic of being able to pause this thing, is I've simply substituted into my formula. Remember, we said X bar was right here. It was my, on average, ate 20 soda cans per day. We got this 95% confidence interval number off of the T chart, the student's T distribution. The sample had a standard deviation of 2 cans. Substituted that in for S. We took a sample of 20 goats. That was the N that goes underneath the square root. So now remember, this is going to be the upper end of the interval, whatever number, because that's the plus side. This is the minus side, so this one is going to go over here. So when I take a look at solving, simply remember that the result of all of this is simply going to be the value on the curve to the right, or the large side. This one is simply going to be the value to the left, or the small side, negative side, that delineates and that indicates that 95% confidence that the mean number of cans eaten by all of his goats, the goat population will fall between this lower number and this upper number. Let me do some math real quick. All right, all I've done now at this point is I simply took 2 divided by the square root of 20, gave me this 0.447. I'm going to multiply it by the 2.093. Remember, that's the number that we got from the t distribution, 95% confidence interval, 220, that's horrible looking, minus 1, my 19 degrees of freedom. So now that I've taken that that piece of math, 2 divided by the square root of 20 times my 2.093, I end up with this. Remember, this is going to be this side over here to the right is going to be this. Remember, this is always my positive side of the curve. This is always my negative side. So I'm going to add to the mean to come up with this value. I'm going to subtract from the mean to come up with this value. And what I know is I now know the 95% confidence interval for the mean number of cans eaten by the entire goat population. Alright, so now that I've done that, what I've come up with the 95% confidence interval. It's between 19.06 and 20.94. That means is there is a 95% probability that the true actual average number of cans eaten by the entire goat population per day is between 19.06 and 20.94. There is a 0.025% chance that I'm either off on the upper side or up on the lower side, because remember that 95% is in the smack middle of the distribution, and if I want to be more certain than that, then I've got to change that confidence interval percentage to go to, say, 99% or 90% or 80%. But we solve these the exact same way that we did knowing the standard deviation of the population. Only difference is these are with a twist or a t, because I only have the sample standard deviation, not sigma. It's been great spending time with you guys, and I will see you around the camp.
Hey ladies and gentlemen, it's Professor Williams again, and we're going to look at confidence intervals for the mean. We're going to run a one sample t-test, and we're going to use Minitab to do it. 10 randomly selected people were asked how many pictures of quokkas they had seen on Facebook in the last month. So it was reported that the mean number in our sample was 7.1 with a standard deviation of 0.78. Now remember, this standard deviation is the standard deviation of this sample of 10 people. What we want to do is we want to find the 90% confidence interval of the true mean number of quokka pictures seen on Facebook. Because our sample size is only 10, we have to have an assumption of normal distribution so that we can apply the central limit theorem. Remember, since the population standard deviation, or sigma, is unknown, we're going to substitute the sample standard deviation for it, and we're going to use a t distribution with n-1 degrees of freedom when we construct this confidence interval. So let's go over and get Minitab to help us. So here we are in Minitab, and we're going to come up to the Stat menu and come over to Basic Statistics. And remember, because I do not have the population standard deviation, I only have the sample standard deviation, I'm going to run a one sample t-test. So now that I have this, I don't have raw data, I have summarized data. And the question told us that we had randomly selected 10 people, and X bar, or the sample mean, was 7.1. We had a sample standard deviation of 0.78. And now I have to come to my options. So the confidence level that we had been asked about was 90%. And remember, when we're constructing a confidence interval, we always want this alternative to be mean not equal to, because that gives us both sides of the interval. And I'm going to hit OK. And now I'm going to hit OK again. So Minitab thought for a second, based on a sample size of 10 with a mean of 7.1, sample standard deviation of 0.78, calculated our standard error of the mean, simply took that standard deviation divided by the square root of 10, and it gave us our 90% confidence interval for the population mean. So now when I come back and I looked at it at my curve, what I ended up with was a confidence interval between 6.648 pictures, 7.522 pictures. Remember, this was simply my point estimate of x bar plus an error minus an error. And so now how do we interpret that? We are confident that 90% of the intervals constructed from our data will contain the true value of the population mean. Only 10% of the time will the true population mean be above or below this, and this will happen 5% of the time it will be higher, 5% of the time it will be lower. As always, I hope that you found this useful, and thanks for watching.
Hey ladies and gentlemen, it's just me, and we're going to do confidence intervals using Minitab today, and I have a picture of a jump roper because we're going to deal with jump rope data. So we're going to go over and open up Minitab into a new worksheet and see how this works. Alright, so here we are in Minitab, and what I've got is a open worksheet that has data here for number of jumps. What these number of jumps are is there was recently a jump rope contest in California, and they recorded the number of times that individuals could jump a double jump rope. And so I have recorded here, I believe, 60 observations. So we're going to begin to calculate a confidence interval for the sample of these 60 entrants in the jump rope contest. So I'm coming up to stat, and I want basic statistics, and I want to display the descriptive statistics, and I get this great dialog box, and it shows me the variable I have available is C1, number of jumps. I'm going to select it so it jumps over here, and I'm just going to see what statistics I'm going to get, and I can just use the default, which is the mean, standard error of the mean, standard deviation, the quartiles, and this is just the default. So I'm going to click OK, say OK, and you'll see here that it gives me my mean, the standard error of the mean, standard deviation, all the information that I need. Because what I'm really here to do is to calculate a confidence interval. So I'm going to go to Stat, go to Basic Statistics, and what I have is I have one sample of jump ropers. So I have a one sample t-test because this is just a sample. So I'm going to select one sample t, get my box, double click number of jumps so it comes over here. Whoops. Double click number of jumps, and I need to tell it in options, I need to tell it what confidence level I'm going to test at. So first I'm going to do 95, which is the default, and say OK. I'm going to say OK. It's going to come up with this confidence interval, which says there's a 95% probability that the true mean of number of jumps that somebody could do on a double jump rope is between 41.1 and 53.79. So I would say that it's between 41 and 53. The other thing that you may want to do is to come up here to graph and to use this one here that says probability plot, because we want to see, was our data relatively normal in order to make this leap to confidence intervals. I'm going to say OK. I'm going to graph the variable number of jumps. I'm going to say OK. Look at my normal probability plot. I've got a couple down here that are a little bit strange, but for the most part, the rest of them fall inside this normal probability plot. And so I'm probably going to get away with it, primarily because I have a n, or a sample size of 60. So I'm going to get rid of that. And so now I could go back and I could do stat, basic stat, one sample t-test. Still has my number of jumps. I could go to options. I can go to a 99% confidence level, say OK, say OK. And what we see is that as our confidence increases, the width of our interval increases. I went to 39, really from 39 to 56, as opposed to 41 to 53. So if you're given just raw data, come into your stat, calculate your basic statistics, then come back to basic stats, come down to your one sample t, and you can find your confidence interval for any level of confidence that you need to work with. So, see you guys later. All right, I'm going to work this problem on this chapter quiz that has given everybody such fits. What we have is I have a survey of 50 retail stores, and that survey revealed that the average price in the microwave was $375 with a standard error of $20. I'm going to assume normal distribution. I want to know a 95% confidence interval to estimate the true cost of a microwave. Well, what I have done is I have accumulated some information that I'm going to need to solve this problem, first and foremost. I've gone through, and this is what I've gathered. I've gathered that 50 represents my value for n. It's the number in my sample. The average price of the microwave was $375, which gives me X bar. Standard error is $20. Now, for this one, if you go back into your text, it will show you that the standard error is the exact same thing as S. So if you're given standard error, it's the same thing as being given the sample, and I mean the sample, standard deviation. Since I had S, sample standard deviation, I immediately went and I pulled the t distribution to construct my interval. Anytime that you have sample, you use the t. If you can't remember it any other way, remember that after S, the letter T comes next in the alphabet. All right? So, I've gotten together the formula that I'm going to use, and because I'm using T, I know I have to use degrees of freedom. Degrees of freedom are simply calculated as n minus 1. Remember up here I had an n of 50. So now what I'm really constructing is a 95% confidence interval at 49 degrees of freedom. Okay, hang on, and we're going to solve this bad boy. Okay, magic. Here we go. What have I done down here? First thing I did was I broke this formula into two pieces because it's a confidence interval. That means it has an upper side and a lower side. The plus is the upper side, the minus is the lower side. So I've simply taken that plus and minus, I've just broken it into these two formulas here. Now, what have I also done? I've gone ahead and set up the first one for you, and all I've done is substituted. I had X bar. I took X bar from up here, dropped it into the formula here. I had S here. I went over here. I grabbed a standard error of $20. I dropped it in here. I had N of 50. I brought that around. I dropped it in right down here. So the only thing that I have left to explain myself for is where did I get this 2.010? Where did that number come from for this T alpha? It came from the T distribution table, and I looked at the confidence interval at a 95% level of confidence, so a 95% confidence interval, and I looked at it for a two-tailed test, and what it told me was that was 0.05. So I just used the header of that table to find my 95% confidence interval. I simply came straight down to where I saw 49 degrees of freedom, and I plugged in the number I found there of 2.010. So remember, reading this T distribution, go across the top, across that top column, find your confidence interval, which is simply going to be given to you, however much it should be. Come down the chart until you get to the row that has your degrees of freedom on it, and drop that number right in. So when I go to solve this other side, this lower half of the confidence interval, all I'm going to do is I'm going to take this exact same calculation here, whatever this all calculates out to be, and I'm going to end up dropping it in right here. So this and this, those are some wild arrows. Trust me, it's all the same. Let me show you. See, I told you it was all the same. I simply took everything that was up here, moved it down to this lower confidence interval. Only difference is going to be, instead of adding that number, I'm going to end up subtracting it. So let me type a little math here, and I'm just going to show you how I solved to determine what I had to add and subtract from my value of X bar. I'm going to take my $375 and I'm going to add it to 2.010. I'm going to multiply that times $20 divided by the square root of 50. The square root of 50 is 7.071. Now I'm simply going to take 20 divided by 7.071, and I'm going to come up with 2.8284. So the way that's going to look is it's going to look like $375 plus 2.010 times 2.82845 if you're like crazy about decimal places. I'm simply going to take and make that multiplication one more time, and I'm going to get $375 plus 5.685 rounded to $380, and I'm going to round all the way up to 69 cents. That is the top of my interval. Come down here, do the exact same thing for the bottom of my interval. Now the nice thing is that I don't actually have to calculate this again, do I? Because this part of the formula here is the same as this part of the formula. This part of the formula solved to 5.685. I really don't want to do my math twice. So instead of having to do the math twice, once I've calculated one side, either upper or the lower side of the confidence interval, look how I can solve it now. All I have to do now is say 300 and, I'm going to get my cursor to work. All I have to do is say $375 now minus, because this is the lower end of the confidence interval, I'm going to subtract 5.685 from it. And when I get that, that will give me the lower end of my confidence interval. Remember, with a confidence interval, it's just that. It's always an upper and a lower number. And so what I'm going to end up here is I'm going to end up with $369.31. All I simply did was, instead of doing math twice, is I simply took this 5.865 right here, and instead of adding it, I took it over here and I subtracted it to give me the lower end of my interval. So what does that give me? It tells me that the 95% confidence interval of the true cost of a microwave oven is $369.31 to $380.69. Hope this helps, and I will see you guys around Blackboard. Welcome back, all you fans and friends of business statistics. We're going to talk about confidence intervals for proportions. They work very much like confidence intervals for the mean, except we're going to use proportions. And this little guy on my screen is a wombat, and the reason he's there will become somewhat obvious in a moment. All right, so what do we need to know about confidence intervals for proportions? We need to know that there's some really good news. One of the pieces of great news is that we are back to standard confidence interval values. Because we are using a Z alpha 2 for these, we can go back to these standard intervals where we have 95% equals 1.96, 80%, 1.28, and so forth. So that's the great news. The other great news is that proportions are really nothing different than some pretty fundamental percentages or probabilities. The proportion is nothing more than the percentage of the population or sample that has the characteristics that you're interested in. So if I randomly survey 100 people and ask them what percentage of them went as a serial killer for Halloween, and 10 of them say they did, then 10 out of 100 is my proportion, or 10%, which is probably higher than you would actually have gotten. So I'm going to use these standard confidence interval values. I'm going to remember that a proportion is nothing more than what we're interested in, characteristic we're interested in, divided by the total number of people either in our population or our sample. So let's work a fast problem with this, and I think you guys will really get the hang of this because you're already good at the other confidence intervals. Okay, this is fundamentally just the curve, and the way that this curve works for these 99% confidence intervals. We know that we have 49.5% of the data on the left side, which is the negative side of the curve, 49.5% on the right side, or the positive side of the curve, making up the total of my 99% confidence interval. I'm solving for a lower interval level or boundary and an upper confidence interval level or boundary, which means that I have 0.005 or 0.005% of my data falling in these two tails right here. Out here in these 0.005, those are my probabilities of missing the true proportion of the population when I come up with this estimation of this confidence, 99% confidence interval is going to fall between the upper boundary here and the lower boundary here. So, how do we do that? Let's take a look at this problem. Problem says that the owner of a local pest control business wants to determine the proportion of homeowners who are infested with wombats. So he randomly selects and surveys 100 homeowners, and very surprisingly, he finds that 80 out of 100 of them are having trouble with wombats at their homes. He wants to be certain that he has enough wombat traps in his truck, so he has asked you to construct a 95% confidence interval for the true proportion of the population who experience problems with wombat infestation. So, let's see, what do we have? We're trying to estimate this proportion right here in the center. We're looking for P, or the proportion of the population. So, what do we have? We have 80 out of 100 are having trouble. So all of a sudden I know that that P is equal to 80%. So last time I did my math, 80 divided by 100 was 80%. I want a 95% confidence interval, so I'm going to take that Z alpha, right, off of my standard chart. I'm going to know that this value for Z alpha for 95% is simply dropping in our friend 1.96 here. We already know N, don't we? I know N because how many people did he ask about wombat trouble? 100. So I have 100. And I also am able to calculate 1 minus P, aren't I? Because if P is 80%, then 1 minus P, 80% minus 100 has to be, you got it, 20%. So, let me drop some of this stuff in and see what we come up with. And this is what we look like when we get done. Remember, we simply took the P, we took that 80 divided by 100, that became P here, P here. We took the 95% confidence interval, so that 1.96 here, 1.96 here. The only other thing I had to do to the formula was 1 minus P. Remember we said that P was 0.80. 1 minus P has got to be 0.20. So now just make sure that you get your order of operations here correctly, because the first thing that you're going to have to do is multiply this 0.80 times the 0.20, divide it by 100, then take the square root of it. Multiply that times this, add it to this for the, remember, the upper side is here. Do the same thing here, except subtract it, because the lower side of the curve is here. So this left-hand side of the formula is going to give me the value for that lower level, or the lower end of the confidence interval. This upper or right-hand side of the formula is going to give me this upper or highest end of this 95% confidence interval. So I've done a little bit of math magic here while you all were getting a snack or whatever, or I guess I was getting a snack. And everything under that radical of square root came out to 0.04. So now I'm just going to continue on into my formula, multiply that times 1.96. According to my magic calculator, I get 0.0784. Look like it to me. The nice thing is that once you calculated this little piece of the formula here once, I mean, it's obviously the same on this side, since the distribution is normal and I have the same amount of data on the left and the right. So personally, I only do that math once. And then I'm going to subtract it from that P equals to 0.80. Remember, we got that over here from my 80 out of 100 people with the wombats. And now this will solve for me the lower limit and upper limit of the 95% confidence interval for the true proportion of the population who are infested by wombats. All right, ladies and gentlemen, we're going to do more confidence intervals using Minitab. All right, so we're going to take a random sample of 150 people who are spectators at a jump rope competition. We're going to ask them if they could jump rope for 15 minutes without either falling down or falling out. And 60 of them actually say yes. So the question is, can we construct a 95% confidence interval for the actual proportion of people everywhere, i.e. the population, who can jump rope for more than 15 minutes? And we can, because we can say that p hat plus or minus z alpha divided by 2 times the square root of p hat times q hat divided by n will give us that confidence interval, where we know that p hat is the proportion of the population that has the characteristic we're interested in, which in this case is going to be the 60 out of the 150. And we're going to calculate this 95% confidence interval, which means we're going to use a z alpha 1.96. And we have a sample of 150 people, which is n. And we know that to get q hat is simply p hat's evil twin. So if we take q hat, will equal 1 minus p hat. And so we can plug all of this information here into this nifty formula here, and we can come up with the confidence interval, or we can jump over and open Minitab and get it done in about half the time. So here I am over in Minitab again, and I'm going to come up to Stat. I'm going to come back to Basic Statistics, and I only have one sample, don't I? I only asked 150 people that one jump rope competition, and so I know I have one sample, and I asked you to give me the 95% confidence interval for the proportion. So I'm going to select one proportion. Oops, sorry, that was Wanda jiggling her tags. One proportion. So I'm going to get this great dialog box. And this time I don't have samples in columns. I have summarized data. And what I told you was that 60, which is my number of events, out of my number of trials, 150 were the people who could jump rope for more than 15 minutes. Remember, we want to go to Options, and we want to specify the confidence interval. And in this case, default is 95, and we want 95. So we're going to say OK. Come back to our original dialog box. We're going to hit OK. And it thinks for a second, and it tells us that based on a sample of 150, where 60 of our people said yes, they could jump rope, gave us a sample proportion of 40%, which I know is correct, because if I take 60 divided by 150, I get 0.40. What I know is that the 95% confidence interval for the true proportion of people in the population who could jump rope for this long is between 32% and 48%. So I know that based on my p hat equal to 0.40, that somewhere between this 32% and this 48% lies the value of p, which is the population proportion. So I think this was a lot better than the formula, and so what we all know is now we love Minitab. I will see you guys soon.